Welcome to a problem solving session for the course Linear Algebra. I am Siddhi Balu Amboli from IIT Gandhinagar, and today we will discuss problems related to span of vectors, linear independence and linear dependence of vectors. So let us start with the first question. That we have to check true or false. The vectors p is equal to 130 and w is equal to 111 in R3 generate the subspace U is equal to AB0 such that A comma B in R of R vector space R3. So any guesses for this? So what we need to do is we have given two vectors V and W, and we have to check whether these two vectors generate this subspace U. So they have already given that U is equal to AB0 such that A comma B in R is the subspace of R3 as R vector space. That's okay. And what we need to check is whether this U is generated by this and 1, 1, 1. I hope you know what this means. So when we say that something is generated by certain vectors, it means that, so we say that let U be a subspace of let us say K vector space V if of K vector space is generated by V1 to Vn if for all V in V for any vector, or let me write in one, for any vector V in V there exists A1 to An in K such that V is this A1 V1 plus An Vn. Okay, and when this V1 to Vn generate the whole space V, then we call it as a generator of vector space V. So V itself is a subspace of V, and when the set generates entire V, then we call it as a generator of set V, subspace V or space V. Okay, so what we need to check is whether this U, so what we need to, and when we write this, if you notice, this is also written as something like this in notes. They are writing this as kx1, kxn, and so on. So kx and so on. Okay, so something like this is written in the notes, and what it means is when we write this kx1, it is actually collection of all elements of this form. This for x1 in V. Kx1 is set like this, x1 such that A is in K. Okay, and when we write this k x1 plus k x2, it is collection of elements of this kind. A x1 plus b x2 such that A and B are from K. So it is collection of all the possible linear combination of this element. And in general, we can write something like this. It means the all possible linear combinations of x1 to a xn. And we are just changing the coefficients of x1 to xn. So this is just a1 x1 up to an xn such that ai are from K. Okay, so what we need to check is whether this 1 and 3, sorry, this 2, U and W here, or V or W given here, whether they generate my entire space, U or not, this space. So what we need to do is we have to start with some element from my set U, or from my subspace U, and then check whether I can write that element in this form, whether I can find some coefficient such that uh, the linear combination of those V and W will give me my element from set subspace U. So let U belongs to U. Then we know that U is of this form, right? U is some A comma B comma 0, where A comma B belongs to U. Sorry, A comma B belongs to K. Okay, and what we need to find is, so we need to find, I'm writing this P and Q such that P and Q in K such that U is equal to, yeah, let it be. U is equal to PV plus QW. So what does this mean? AB0, I need some to check whether this is P130 plus Q111. So what does this mean? AB0 is, if I multiply and combine the, so if I solve this, I get something like P plus Q, comma 3P plus Q, comma Q. Okay, and this implies my P plus Q is A. I need 3P plus Q to be B, and I need Q to be 0 if I compare both the sides. By comparing, yeah, both the sides, I get this. So once I have Q is equal to 0, this implies P is equal, this implies that 3P is equal to B and P is equal to A. So this implies this implies P is equal to, we need to find P, right? So P is equal to B by 3 and P is equal to A. And if, so there are two possibilities of P, but it does not really help us, because if that is the case, this implies that this A has to be B by 3. If 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 such P exists, then this B by P A must be B by 3. But this, we do not have any restriction on this A and B, right? So what I'm saying is, if such elements exist, then it will be of this form. So what they are saying is Q will be 0 and P needs to be one of this. So all the elements are of this form. P 3P comma 0, because my original element was this U here. So U is of this form. And but so in particular, if we choose U is equal to 110 in U, then this 110 is not a linear combination of this 130 and 110, sorry, 111. Since if because if 110 is 130 plus some, not a, let me say 11, then this will imply Q has to be 0 because last coordinate needs to be 0. So this implies Q is 0 because last coordinate needs to be 0. And but then this gets 110 is equal to P comma 3 P comma 0. And then this implies P is equal to 1 and P also is equal to 1 by 3. So this is not possible, right? This is not possible. So we have particular element from space U which cannot be written as linear combination of this U and W. So we can conclude that this V and W do not generate the subspace U. So hence U, hence V is equal to 130 and do not generate.
Ma'am,
Yes,
so
this W is not in the space U. Yeah, you were saying something?
ma'am, so to solve this, we had to first simplify it to like that PQ point, like P comma, like P equals this, Q equals 0, and after that we had to find a counter example to prove it's not. Is that?
So, oh, so you're saying that whether we need to explicitly find P and Q and then find the counter example. See, we could have find the counter example in the first example itself because in the first trial itself because uh, just a second, do not generate U. Yeah, so see, if first of all, just observe that uh, when we write this U and U is this set, right? A B 0, A comma B in K or whatever field R, I think. ठीक? Okay. And we have V as 130 and W as 111. Okay. So just observe that this W does not belong to my vector space U. Okay. W does not belong to U. So if I want to write it as linear, so whenever I want to, so if at all there exists some element, I mean, if you want to write some uh, element from U as a linear combination of V and W, then this won't be much helpful for us because W will always, third coordinate of W, if we check, it's 1, it's non-zero, but in U it is always 0. It is A comma B comma 0. So it is always 0. So the coefficient of this W is always 0 in linear combination. And then only element left is V. So if I look at the linear combination of V and W inside my set, uh, inside subspace U, then it will just be so it will be just KV plus 0W. This will contained in U because the moment I take some non-zero coefficient for W and I mean some non-zero multiple of W in, I mean, some A W does not belong to you for any non-zero A. Okay.
Ma'am, one more thing. Ma'am,
Yes.
when we say r to the power 3, that means the space r is multiplied by itself 3 times. But I'm having a hard time understanding what exactly that looks like. So if you could just explain that, that would be great.
Could you please repeat the question? You are saying that you are not able to understand how R3 and R are working.
Yes,
Is
ma'am.
that
That's
your...
the question. Yes, ma'am. Exactly.
So you are saying that you R3 is this set A, B, C, such that A, B, C are from R, right? And then when we say that, so what is your question? You are not understanding the vector space structure of R3.
Ma'am, exactly.
Okay, so what vector space has is vector space first of all has two operations. So vector space has uh, two operations. First is addition and second is scalar multiplication. And yeah, so this addition, so if you look at the definition, the way we have defined vector space uh, in the lectures, they say that with respect to this addition, this R3, I mean, for example, so V is a vector space, has vector space V has two operations. So addition is defined, so what they say, V is a commutative or abelian group uh, under addition. Okay, so you know the group properties. So the addition has, uh, and second is that we have scalar multiplication, and V has scalar multiplication coming from where scalars are coming from over K, okay? Coming from this K. So when we say R3 is a R vector space, the addition is as usual, what we do coordinate wise. For example, if I take this A1, B1, C1 and A2, B2, C2 from R3, then their addition is just coordinate wise A1, A2, B1, B2, C1, C2. Okay, so addition is not a problem. Okay, it's there. So what you're saying is why R is a scalar. So if I take this, and when I say R is a R3 is a R vector space, it means I'm having this operation here, R into R3 going to R3. This map defined like any C, or let me take alpha here, or let me take D. ABC is going to DA, DB, and DC. And this is my scalar multiplication. This element still land inside R3. So that's why this R3 is a R vector space. So you understood, like, the only this, yes, yes, your question is now.
Yes, ma'am. I got it, ma'am.
Yes, and see, this scalar multiplication should make sense, okay? I mean, uh, there are few properties it must satisfy. For example, when I multiplied by some scalar that again must land in R3. For example, if I talk about R3 being C vector space, complex vector space, then it does not make sense because see, R C cross R3 goes to R3. So this is my vector space, okay? This is my vector space V. This is my vector space V. I am writing this as R3. And then this is my field C. Okay, and if I define this A, B, C from here to here, this DA, DB, and DC, it looks like it makes sense, but it does not really belong to R3. So for example, if I take I from here and take ABC, then this IA, IB, and IC, this is not element of R3. So R3 is not a C vector space. Under under this scalar multiplication defined above. Is that okay?
Yes, ma'am, it's clear, ma'am.
Okay. And but if you take instead of C, if you take set of rational numbers, then it will be a vector space. Because in that case, this Q, I mean, it will still land in R3. So then R3 is, if I take Q instead, so R3 is a Q vector space under scalar multiplication defined earlier. So the scalar multiplication, so when we say some V is a vector space over something, that field only we need for scalar multiplication and look at the span and everything. And mm, and for not, I won't say for nothing else, but the essence of field being there is for scalar multiplication. This addition follows all the properties of group, and yes, that's it. I hope it is clear. I mean, you understood like it means to what it means that something is a vector space over some field.
Yes, ma'am. Thank you, ma'am.
Yeah, sure, sure. So, you understood this as I hope this was clear. So this is not true, okay? So this is false because the given space, uh, given elements U, this V and W does not generate my U. And if we want to find what are the generators of U, then so let us. So if you look at this, U is what my ABC, sorry AB0, such that A and B from R3. So if I take, let U belongs to, no, no, yeah, let U belong to, U is equal to AB0 belongs to R3. Then if I want to find its generator, then I can simply do this. And this will imply that U is generated by these two elements. And this is just, or we can write something like this. But this is just one kind of generator of this U. Okay, there are many. For example, if you take this, let my V be 1, 2, 0 or 1, 3, 0, let me take, and W be 1, or let me take anything would work other than 1 and 3. So let me just take this only 1 1. Not anything would work other than 1 and 3. Anything which is not a multiple of 1 and 3 with third coordinate 0 would work. So if I want to, so we can check that this actually forms, this actually generates my u. For example, if I take any a comma b comma 0 from here u, and if I want to find some p and q here, then what it means, I need this a comma b comma 0 is equal to p plus q, p plus, sorry, 3p plus q comma 0. So this implies that a p plus q is a and 3p plus q is b. So this imply my, if I try to solve this simultaneously, I get 4p, sorry, I get 2p is equal to b minus a. And the moment I have 2p is equal to b minus a, this implies p is equal to b minus a by 2. And once I have this will imply that p plus q is equal to a will give me b minus a by 2 plus q is equal to a. So q will be my b minus a by 2. It will be minus, right? This minus and this plus. Or let me just write a minus b minus a by 2. And then this gives me that any element, this a comma b comma 0, can be written as this. P was my b minus a by 2. It was 130, right? Yeah. 130 plus this element. We can solve this, right? This is 2a minus b plus a by 2. This is 3a minus b by 2. 3a minus b by 2. I think we took 110. And you can just solve and check that this, therefore this was element from u, and this is from linear combination of R130 plus R110. Okay, so these two elements are, so what this imply is that any element if I take from u, it belongs to this set. And anyway, this set, so understand that when we wrote this, when we have this implies that u belongs to u actually belongs to this set K130, sorry, R130 plus R110. So this implies u is contained in this set generated by 130 and 110. This still does not prove that this is exactly equal. But you can just see that 130 belongs to you and 110 belongs to you. And then if you remember some exercise from one of the exercise from last week, that their linear combination will also land in that U. So this will imply that this K130, this R130 plus this R110 will be subset of this U. And this two here, this one and this one, if I make, then 1 and 2 will imply that U is actually generated by these two elements. So just showing that some element from U belongs to the linear, can be written as linear combination of two elements, still does not prove that it is equal to it. It just proves that it is contained in that set. I hope it is clear what we did so far.
Yes, ma'am.
Okay. So, so those who are not here, what we did was we just tried to solve this question. The vectors were V and W, and we wanted to check whether uh, this is my V and this is my W, and we just wanted to check whether this U is a subspace generated by this U and W or not. Wait. Yeah. So what we did, we tried to calculate, we tried to find whether we can write it, but then it did not make sense because we arrived at this condition that P is equal to B by 3 and P is equal to A. So this need not be true in general. So U cannot be written as any element, any general element of U. We could not write it as a linear combination of this V and W. This was V and this was W. And for example, if we take this element, that's what we try to do. If we take this element 110, then we saw that we could not write it as a linear combination of those two vectors there. And that's it. But then we try to find if given elements are not the generators of my given subspace U, then what it will be. And so in general, we could just find this set uh, of 110 and 010. This generates my vector space. But understand that the generators of a vector space need not be unique. We can have multiple different kind of sets which generate uh, my subspace, and that's what we did. We saw that this set generates my vector space U, vector subspace U. But along with that, we also saw that there is one different system of generator which generates my U. For example, if we take this 130 and 110, it generates my subspace U. Okay, this was what we did so far. And yes, so now if there are any doubts, please let me know. Otherwise, we will move to next question. Yeah. So let us start with second question, that for n in natural number, we define this set Pn, just Pn, which is actually this Pn x comma k. This is zero union all those polynomials in K is such that degree of this f x is less than equal to n. Let me just write it here. This is how I'm defining this set Pn, and then and this is also true or false. Let me just write it. Then the K vector space P3 is generated by A x bx square plus 1 x square plus x cube, where A and B are fixed non-zero elements of K. Okay, so this is what we need to check. So what is the question? So we are given, so this is how Pn is defined here. Pn is collection of all the polynomials of degree less than equal to n. And we have to check now whether this is system of generators or yeah, system of generators of this K vector space P3 or not. So what does P3 means? P3 means it is 0 union F in Kx such that degree of Fx is less than equal to 3. Okay, and why we need this 0 here? Because uh, it is difficult to define the degree of 0, because when we talk about a degree of some polynomial, what we say that uh, highest degree with terms in the polynomial, we check the we check their degrees and we say that the highest which has non-zero coefficient. But for 0 we do not have anything non-zero, so it's difficult to define the degree of 0. But in most of the cases, as per the need of the proof or the argument, the degree of 0 is considered either 0 or minus infinity. Mostly it is considered as minus infinity. And yeah, that's it. So that was just extra thing. But for now, we are including this 0 here and assuming that it's because otherwise, if we are just considering polynomials uh, with degree, the well-defined degree less than equal to 3, then 0 won't be there and we need to have 0 in the vector space. So yeah, that's it. So now what we need to do, what we need to check is whether this P3 is generated by this set. Let me just write this as a comma x comma b x square plus 1 and x square plus x cube. This a and b are fixed and non-zero, okay? Fixed and non-zero. A and b, sorry, a comma b are fixed. And we have to now check this. So what it means to check whether P3 is generated by these 4 elements, I need to start with some element from P3, and then I need to check whether I can write it as some linear combination of this given 4, what we say, given 4 vectors. So let me just give them name, this V1, V2. Let me write, this is my V1, this is V2, this is V3. I'm just giving them name right now. We don't know whether we will be using it or not, but if we need to, then it will come handy. So
Um,
let, yes, sir.
there's a small request. Can you just explain the from the beginning of this question? I just joined and I missed because of traffic.
Okay,
Kindly.
okay, okay. So we are just trying to solve uh, this. Yeah, so we are just trying to check whether this set Pn is generated by. So Pn is defined like this. Pn is a set of all collection of polynomials of degree less than equal to 3 in one variable. And what we need to, so this P3, so in general it is defined for n. So degree of f is less than equal to n. And the
Okay.
question is asked for P3. So degree of polynomial is less than equal to 3. And what I was explaining is that we are including 0 in this set
Mm.
because degree of 0 in general is difficult to define, because how we define the degree. It is, so when we say if we take some polynomial p of x, we write it like a and x power n, so on up to, let us say, n minus 1 x power n minus 1, and something like this. And then we say that degree of x is maximum n, maximum power of x such that its coefficient is non-zero. Uh, so this non-zero-ness of coefficient gives me the degree of polynomial. So when we talk about 0, 0 is also polynomial, right? I mean, 0 also belongs to this set Px. in general. 0 is also considered as polynomial, but we don't know what its degree is because this non-zero-ness of a coefficient, there is nothing non-zero in zero polynomial. So conventionally, degree of 0 is mostly defined as uh, minus infinity. I mean, this is just convention of mostly followed by people. Just the degree was, I will just explain why this 0 is separately written here. Because if you are considering, I mean, if we set this notation degree of 0 to be minus infinity, then we do not need to write this 0 here. But if we are not explicitly giving any, what we can say, a description of degree of 0, then we explicitly need to include this 0 here to make sense that this P3 is actually a vector space. Because 0 needs to be there for something to be a vector space. Uh, yeah, that was something which I was saying. And now we need to check whether this set, we need to check whether this P3, sorry, not this P3, whether this is generated by this, let me just write it like this. I think x, b x square plus 1 and x square plus x cube. I need to check whether this is equal or not. So what it means that this is, or sometimes we also write it as span of this set if you do not know the notation. And when I say span, the span means this is, we are talking about R, right? Or K, any field K, right? So this is KA plus K bx square, sorry, kx plus k bx square plus 1 plus k x square plus x cube, this P3. And I just in first question I told you like what this means. So for any V in V, this KV is actually collection of all these elements. A V such that A in K. Okay, and this is then span of this vector V. And when we write something like this, I already, if I take V1 and V2 from V, then this KV1 plus KV2 is actually span of this two vector space, and it is precisely this set. So it is possible linear combination of these two elements, and that's what something called a span of a given vector, a span of given vector space means. And when we say that some given subspace is generated by uh, some set of vectors, for example, here we have these four vectors here from vector space. We say that P3 is generated by these four if span of this four element is exactly equal to this P3. Okay, and that's what we're gonna do. We will start with some element from P3 and we will say that we can write it as some linear combination of these four elements if we can. Okay, so let us take some f of x in P3. So this fx will look like this, right? Fx will look like what? Let me write it like this. Let me use f itself. F naught plus f1x plus f2x square plus, I don't really want to use f1, f2, f3. What variables would work? Let us take c, d, e, f. C plus dx plus ex square plus f x cube, right? This is how some polynomial in degree, and where this c, d, e, f belongs to my k. Okay, the coefficients are coming from k. This p and 3k, the k is, we are ignoring the k because we know where the coefficient, from which field the coefficients are coming from. And now I want to check whether, okay, I anyway have to use the index now. Let us see. So c plus dx plus ex square plus fx cube. And to check whether it is linear combination of these four elements. So let me just write this. C1 plus C2x plus C3 x square plus C3x cube. Ci belongs to K. And so C1 plus C2x plus C3x square plus C0, 1, 2, 0, 2, and 3. This A into D0 or D0A plus D1, I think it is X, D1X plus D2 x square plus 1 plus D3 x square x cube, x square x cube. So this will imply that C0 plus C1x plus C2x square plus C3x cube is equal to, if I combine coefficients of all the xi's, it will be D0 A plus this D2 into 1. So this C0 is C0 into 1 if we check. And for x, I have only D1x, so nothing. For D2, for x square, I have this D2 plus D3 x square and D3 x cube, right? I hope I did not miss anything. So if I compare the coefficients, I get C0 is equal to D0 A plus D2, C1 is equal to D1, C2 is equal to D2 plus D3, and C3 is equal to D3. Or if I just shift it from here to here. So I wanted to find this DI. We want to find DI because then that will uh, what I can say, that will give me the coefficients needed or coordinates needed to write the given element as a linear combination of this V1, V2, V3, V4. Okay. So I already have D1 is equal to C1 and D3 is equal to C3. And if I substitute it there, where did B go? Where was B? Oh, bx square. It was bx square here. D. So here it will be bd2. bd2. Yes, nothing else. And if I want to find this other d3, so from d3 I can get hold of d2. So bd2 plus d3 is c2. So I need to find what is d2 is. So d2 is equal to c2 minus d3. So this is c2 minus c3 and this is still b. So d2 is c2 minus c3 divided by b. And this makes sense since b is non-zero. Okay, now I have hold of d2 and I can use it here. And then this will imply d naught a. So I have now d1, d3, d2 and d naught a plus d2 is c naught. Then I get d naught is equal to c naught minus d2. And this will imply that d naught is equal to c naught minus d2 by a naught. And a naught not a naught, a. And a is non-zero, that's why this division makes sense. And we actually got everything. D2 we already know what it looks like. It is this C2 minus C3 divided by B by A. So this is B C naught minus C2 minus C3 divided by AB. So yes, so we have D naught here, we have D naught here, we have D2 here. We already have information about D1 and D3. Or let me just write the whole box. And here also. Uh, and now this gives me that any element, and note that these DIs are all of, it contains only, so let me write this. DI, the expression or yeah, expression for DIs contain only A, B, and CIs, which are fixed. Okay, the moment I said I need to find uh, whether some polynomial f, I want to write it in terms of the linear combination of v1 to v1, v2, v3, v4. I'm fixing that polynomial first, and for that polynomial, I'm trying to find the coefficient. So when I'm fixing f here, I'm fixing this CIs here, and I wanted to find these coefficients D1, D0, D1, D2, D3. And I got this information or the expression for DI in terms of these CIs and AB. AB was anyway fixed in initially. So therefore, this P3 is contained in now this span of KA, KX. This is not really, let me write this, KX plus K bx square plus 1 and k x square plus x cube. Okay, and now we know that this A anyway belongs to P3. This polynomial x belongs to P3. This bx square plus 1 belongs to P3. And x square plus x cube belongs to P3. So when I write this span over K of A, x, b, x square plus 1 and x square plus x cube, I can say that it belongs to P3. It's contained in P3. And the moment I have all this information, I can say that P3 is exactly equal to this span of K, A, x, b, x square plus 1 and x square plus x cube. Okay, is this okay? And therefore, P3 is generated by ax bx square plus 1 and x square plus x cube. And note that this a and b being non-zero, which is given in the question, we also use that. This a and b are non-zero. Okay, we use that because otherwise dividing by this ab here and here, it won't make sense. Okay, it won't be well-defined expression otherwise. Is this okay so far? Okay, so now let us move to next question. Any doubts?
Ma'am, just to recap, here we
Yes,
fixed
yes.
the polynomial beforehand. So we can take our liberty in fixing a polynomial, like we're allowed to do that.
Uh, which this one?
Yes, ma'am. So we can just, yeah, so we can just define any polynomial with degree equal to 3, right?
Yes, this is some polynomial in degree 3. This is general expression of polynomial in degree 3, where the CIs are from this base field K. Yes.
Okay, ma'am. Yes, ma'am. I
So
got
we
it.
are choosing some polynomial. So for example, if I say that, for example, we know that R2 is generated. What I'm trying to say is that this P3 is generated by this. So we got general expression like this of D1 being this of this form. So suppose, so let me tell you what we are doing exactly. So let me just write it down again. So my D1 was C1, D3 was C3 if I'm not wrong. D2 has this expression C2 minus C3 by D2 is C minus B by something like that, right? C2 minus C3 by B. Okay. C2 minus C3 by B. And D4, sorry, I think D0 was this. Let me just copy it from here. Okay, this is here. So when I say, so let me take any polynomial. So let us, they say that A and B are fixed. So give me A and B. So let me take A to be some 1 and B to be some 3. I don't care what it is. And if take any polynomial, let f is equal to some polynomial in P3. Let us take it to be what we can take. Any polynomial we can take. We do not need to think much actually. Let me take this 7 plus 6x plus 5x square plus 4x cube. Okay, this is my polynomial. Okay, this is any, instead of this, you could have taken any polynomial. We do not care. And from what we had started, this is my C0, this is my C1, this is my C2, and this is my C3. So if I want to write this polynomial, this f of x of degree 3, in terms of my, in, if, then this f of x, that is this 7 plus 6x plus 5x square plus 4x cube, is actually equal to, I'm taking this a and b to be 1 and 3. So it is what? It says that it is d naught into a. So d naught into a plus it is d1 into, I think it was x. So d naught into a, d2 into b x square plus 1 plus d3 into x square plus x cube, right? But I'm taking a to be 1 and b to be 3. So in that case, d naught will, and d naught is my this expression. So if d naught is b is 3, c naught is 7, minus c2 is 5, minus 4 divided by ab. Ab is just 3. So this is 10 minus 9 by 3. So this is 1 by 3. I don't know why it is, but it is what? I hope, no, it's not 10. It's 21 minus 1 by 3. So it is 20 by 3. I hope I'm correct here. So this is 20 by 3 into 1 plus d1. d1 is just d1. So d1 is my 6 into x plus d2. d2 is my, d2 is this expression, right? So it is c2, 5 minus 4 by 3. So this is 1 by 3, right? 1 by 3, b was my 3, x square plus 1 plus d3 is D3 is my C3. So C3 here is 4. So this is 4x square plus x cube. And if you simplify this, see, here constant 1 by 3 is coming. So 21 by 3 here into 1 plus 6x, which we can't do much about. This 3 by 3 plus 4x square plus this 4x cube. And this is exactly my polynomial. 7 plus 6x plus this 5x square plus 4x cube. So when I'm saying that this is my general polynomial, it means any polynomial, if I pick it, if I pick any polynomial from P3, it is essentially of this form, right? These CIs are some coefficients from my base field. If I'm talking about Rx, it is, I mean, the coefficients are from real numbers. I can start with this. If complex, I don't care. This is general term. So when I'm saying that I want to find, so I hope you understood what we did here. So when I said that this, so your question was that we are fixing something here. So yes, we are fixing something here because we have to start from somewhere in order to arrive at conclusion. So this was my general expression of any degree 3 or polynomial of less of degree less than equal to 3. And this holds for any a and b and any polynomial. So I hope you understood what we did here. So we actually solved it for general polynomial here. Is that okay?
Yes, ma'am.
I hope you got like what we did when we said that we started with general polynomial.
Yes, ma'am. I understood the general expression.
Yeah, exactly. So, yeah, and if there are any other doubts, please let me know. If not, then we can just move to next question.
Yeah, okay, ma'am.
Okay, sir. So let us start with next question. Yeah. So this is question 3. So they are saying let x1, xn, and x. Let me write this x1, x2, xn, and x be elements of a vector space over a field K. Then, just before we start, so this statement is actually true. So this was true false question, and this is true. Okay, that this P3 here is actually generated by this set here. That's it for complicity. Okay, and yeah. So the question 3 is that we have this x1 to xn and x elements from some vector space over a field K. And then first is that the family x1 to xn comma x1 plus xn is linearly dependent over K, but every n of these vectors are linearly independent over K. Let me write all the questions for now. Then second is show that this x1 to xn x are linearly independent over K if and only if x1 to xn are linearly independent and over K. So they are explicitly mentioning over K again and again. X does not belong to this kx1 plus kxn. And a C is that we have to show that x1 to xn is generating system of V if and only if.
Which question we are trying to solve, ma'am? This is a new
Yeah,
question.
this is 4 point. Yeah, this is new question from this exercise sheet 4.1.
4.1. Okay.
Yes.
Okay. Okay.
Yeah. X1 to xn, and X is generating system of V, and this X belongs to kx1 plus kxn. Okay, these are the questions. So let us start with the first one. So this question is completely related to the linear dependence and linear independence of vectors and their span. So they started with some n plus 1 elements from the vector space, and they are saying that the vector space is over field K. So first question is that a family x1 up to xn, and then they added one more. So these are 1, 2, and n elements, and this is n plus 1, n plus first element, and they are linearly dependent over K. Uh, but they are saying that n of these vectors are linearly independent. So when they are saying this, they are already assuming that these xi's are linearly independent. Okay, so we have to show that. What does first question mean? Let me just copy paste it here. Okay, so to show what we need to show that first thing that this x1 to xn and this element here are linearly dependent. I will tell you what linearly dependent means over K. And secondly, that n of these vectors. So let me write this as set. Every n elements of this set, let me write vectors, are linearly independent over K. Okay, so this is my these are my questions. So first thing we need to do is to check, so what is linearly dependent means. So linearly dependent.
We can say when one vector can be represented by multiplying some scalars becomes another, not
Yes,
scalar. I mean, if the
exactly.
scalar, if we multiply, it becomes a similar already existing vector in the set.
Yes, exactly. So we say that um, this the vectors v1 to vn are linearly dependent if there exists a1 to an in K such that at least one of AI is non-zero, with a1 v1 plus an vn is equal to 0. So this is not very conventional way to define linear dependence. So how linear dependence is defined? They first define linear independence or linear, yeah. So the vectors v1 to vn are linearly independent if
Can we say like this? Vi is equal to kvj, where I and j is not same. I mean, I am just trying to say Vi is a j.
vi is equal to
Vi is equal to some k vj,
not really.
because I'm trying
This
to say
is
here that Vi is basically a k times multiply by Vj is because Vi. So Vi and Vj both are same, but Vj is having a k multiplication scalar with all the elements in that vector, Vj vector. So that
uh,
Vi and Vj are dependent. They are not independent.
that is very particular case. So you are saying that vi and vj are linearly dependent.
Yes,
Uh, if vi you are saying is scalar multiple of vj,
yes.
that is completely true. But when I'm talking about this n vectors where they are linearly dependent and independent, uh, it need not be that case when we have more than one element. For example, if we take this uh, set 110, 100, and 010. So this is not this is linearly dependent set, right? Uh, because this 110 is 1 times 100 plus 1 times 010. But as you said that one of the vi is some kvj, none of
Or
this is
maybe,
not happening for,
okay. Maybe that
yeah.
was very trivial, but any
Mhm.
combination of existing vectors
Yes, 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 definitely, definitely. That's what this statement says.
and their combination will not make another existing vector in that set.
Exactly, exactly. This is what this statement says. Xn to xn are not general. This one. That if x1 to xn are linearly independent, then these are linearly independent, and this last one does not belong to existing one. So that's what you wanted to say, right? This
Yeah,
vi
yeah,
does not belong to kvj. So this is what exactly that other says.
right.
So if I, instead of writing xn, if I write xn plus 1, then this is exactly what you are trying to say, that one of the vi's
Mhm.
is not
Mhm.
in linear combination of the rest of the vectors, right? Yes,
Right.
this is what, yeah, yeah, this is what you wanted to say, man.
Yes,
Yeah,
ma'am.
that's, yeah. So that's there. So let us keep it as it is. So we said that this is linearly independent, if a, if for, if for a1 to an in k.
Just one more thing for
Mhm.
clarification, since
Mhm.
I have picked up this maths after long break of
Yes, sir.
this. When we say this definition, I mean it's
Yes, sir.
whenever we say let x1 xn be element of vector space over a field k, I mean all
Mhm.
the scalars are coming from field k, and k can be a real, complex, rational, irrational, anything like this.
Yes, 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 yes. It could be any field.
K is basically representing any real numbers.
Yeah, if I'm talking about real vector space, then yes. In general, I mean, we can talk about vector space being over field. Field could be anything.
No,
I
when we say field R, I mean it is only a rational number. When I
Yes,
say
R is real numbers.
real
Yes.
numbers, when I say
Yes.
field, when I say vector space over a field C, I am
Yes, exactly, exactly.
then
This
I
is
am
this oh,
then
this
I'm
we then
limited to only complex number.
exactly, exactly. This is what I was this is what we also discussed in the very first question today itself, when we try to do this. So see, we were talking about R3 being R vector space. Okay, so when I do this, I take this scalar multiplication from here and then multiply some element from here and I get this, which again belong to this R3. So when we talk about scalar multiplication, so when, let me use this again. We say that, we say R3 is R vector space or V is K vector space. Then for any V in V, this and some A in K, this AV again belongs to this V.
Hmm.
Okay, this has to make sense. For example, if I take R3 and R, this D is in R and this ABC is in R3, and this DA, DB, DC are elements of R, and then this tuple, this belong to my vector space R3. But again, if I talk about this R3 being C vector space here, then it does not really make sense because see, here I am taking this K as C, V as R3, and again, the multiplication needs to land here. But see, if I take I here and multiply it by any ABC, then this element does not belong to R3. So we can't talk about R3 being C vector space by any sense. It does not make sense. So do you understand when you are saying it is over some field, then when I multiply it by, when I define the scalar multiplication must be closed in this R3. So when I'm taking scalar and multiplying it to my vector from given set, for it to be a vector space over that field, that scalar multiplied new element, that AV here, must land in my given set V again for it to be called vector space over K.
Yeah, yeah. Okay, so my just to confirm once again,
Yes,
if I say
yes,
just a, if we say it's a K vector space, then it can be anything. It can be a real or it can be imaginary or complex, anything.
yes, 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 yes,
No,
sir.
but when
When
I
we say
specify when we specify very specific to real, then it cannot be a, imaginary. It should be all real. And in
ye-
subset of real, when I say it's only a real and Q is what? Rational.
Q is rational, yes.
Yeah. ठीक है, okay.
So when we start, so what we are saying is when we talk about vector space, we need to define its base field or the fields from where the scalars are coming.
Okay.
And we can define any vector space over any field as long as the scalar multiplication makes sense. And when we make such statements that field K, it could be any field, it could be any field. These statements which are given here, they hold true for any field. Replace
They
this
hold
K by
true.
any field.
Okay.
Yeah, yes. And even if you notice in notes, they write that in the instruction section, they say that K be any field, and then they are saying that if I'm writing this bold kind of K,
Hmm.
then it is either R or C.
अच्छा अच्छा.
Okay, this is real numbers and this is complex numbers.
Complex number, yes, yes.
Yes, because there are some things which make sense only when we talk about R and C. Uh, so in that case, they will be like those fields will be mentioned. Everything will be explicitly mentioned, like what is needed and what not.
Okay.
And if you go through all the notes and everything, you will see each and every detail is given there. If K is a field, we can talk about any field. If they are writing this K to be the that bold K field, it means it needs to be either R or C and so on.
Okay.
So when you see such statements and they say that K be any field, then this is true for any field, rational,
Hmm.
rational, complex, real.
Yeah, I mean,
finite fields and
scalar
so on.
can come from any of these.
Any of these
Any
fields,
of these.
yes. But
Okay.
once you want, you if you want to when you are saying that my field is, if I want to choose the field to be R, then give the entire argument in R or in
Ah,
C. I mean, you can
un-
switch, you can't switch
understood.
in between. Yes, exactly.
Because some of the earlier proofs of by professor, it was mentioned in some few proofs. Let's see in the complex number. Let's look at in the rational number. Let's look at the real number, and then the k. I was just I because of I missed few lectures, those I was a little confused that whether k means generic or not. So now
Yes, yes.
clearly.
For this question, it is any general field K.
Yeah, fine.
Yes.
In fact, for
Yes,
any
sir.
of these linear algebra where I am listening from the subgroups and vector space, wherever it comes over a field K, it means the scalar values can come from any of these.
Yes, yes,
Field.
yes. Any field K. Yes.
Thank you.
Yeah, sure. So when we say that something is linear, so we were talking about linear dependence and linear independence. So we say that a vectors v1 to vn are linearly independent if at all I have such expression that a1 av1 av2 plus avn is equal to 0, then each of these coefficient must be 0. That is called linear independence. And we say that something is linearly dependent if something is not linearly independent. So
So,
that's what when say. Yes, sir.
so in the same thing you just mentioned the same equation, but you said AI should not, one of the AI should not be equal to
Exactly.
0.
That's the negation of
At
this
least one of
statement
the
that
AI
A1 to, yes, because here I need all of them to be 0.
be 0.
And when I'm writing the negation of that, that something is not linearly independent, then this is what it means, right? At least one of them should be non-zero.
Hmm.
That's what it means logically. At least one, when I say it could be anything, all of them could be non-zero, one of them could be non-zero, two of them, and we do
Hmm.
not care. But at least one of them should be non-zero. That's my
Condition.
condition for something to be linearly dependent. Okay, so that's what we need to find and we need to work on. So yeah, so my first, so we need to prove that this first is we have to prove that this x1 x2 xn and these are linearly dependent over k. So I need to find such at least ai is non-zero such that if I take this a1 x1 plus a2 x2 plus an xn plus, let me write just a x1 up to xn. If this is 0, then this will, I want this to be linearly dependent. So if I combine them, this, if I choose, if I choose ai to be 1 and a to be minus 1, then, and note that this 1 and minus 1 makes sense in any field. Okay. If field is there, if k is a field, then 1 belongs in that field, right? 1 belongs to k in all those fields. And once I have 1, minus 1 will also belong in that.
Inverse of, okay.
Yes, multiple, no, not, I mean, additive inverse of that field. Oh, do not care. Once 1 is there, minus 1 will be there. Minus 1 is coming from the group structure of that field k. So this 1 plus 1 I need, so 1 plus minus 1 is 0 and so on. Okay, so base is group for field and everything. So if I choose this ai to be 1 and a to be minus 1, then I will get this 1 into x1, 1 into x2, so on, 1 into xn plus this minus 1 into x1 plus xn. I claim that this is 0 for ai is equal to 1 and a is equal to minus 1. So this is what? So now consider this. This you can just understand. So this is equal to 1. If I just combine everything, 1 minus 1 x1 plus 1 minus 1 x2 plus 1 minus 1 xn. And this is 0x1, 0x2 plus 0xn. And this is giving me 0. So I have this AIs such that the linear combination of this x1 to xn and x1 plus x2 plus xn, if I, yeah, so this is my x here, if I call it. So therefore, x1, xn, this are linearly dependent. Any doubts here? We,
Yeah, I mean, since the claim is that it should be 0,
mm-hmm,
we have put the value of AI is equal to 1 and A is equal to minus 1. So
mm-hmm.
since these AI and A has a value, and then only we are getting is equal to 0. But according to definition, if they had to be linearly independent, then all of if they're linearly
There
dependent,
must be
then
0.
at least one AI here, which is not holding
Yes.
true here.
Yes. So
Therefore,
this is linearly dependent. So at least one of the AIs must be non-zero, right? So
hmm.
there are almost, I mean, all of them are non-zero in this case. Okay. Or if you want to find, so for example, if I start with this A1 x1, A2 xn, A2 x2 plus an xn. If I talk about in general, I do not care what these xi's are. And this is here, right? This we want. Okay, so if I do this, a1 minus a x1, a2 minus a x2 plus an minus a xn to be 0. So this imply what? That a1 minus a is 0, a2 minus a is 0, so on, an minus a is 0. Hence, so this will imply that a1 is ai is equal to a. Hence, if we, so this is true for any AI and A. This is true for any AI. The moment I have this condition on my coefficients, that as long as AI, this AI is equal to A, I'm getting the linear combination to be 0. So if I choose AI to be some C. So once I have AI to be C, this will imply A to be C. And once I have A to be C, then all other, so for example, if I say A1, if I choose A1 to be C, some non-zero, okay, then this will imply A has to be C, right? This is the condition which I have. Then this will imply all those A2s to AN, they all will become C. A, I, oh, sorry. This needs to be plus here. And this plus will give me minus A. So this is minus C, and rest are all C again. So this is like general expression. So instead of 1 here, you could have chosen any non-zero element of a base field. As long as my A becomes minus of that C, I'm getting a non-zero linear combination of this n+1 vectors such that their linear combination is 0. And that's why this forms linearly dependent set of vectors. Is it okay? What I'm saying is here this 1 and -1 might look ambiguous. Not ambiguous, I mean it looks very particular because the statement is very general. So if you want to find the coefficients, then it becomes easy that all this AI must be minus A, and we get the coefficients here such that the linear combination of this n+1 vectors is 0. Is that okay? If
I
there is
mean,
any doubt, yes, sir.
up to it is clear that it is AI is becoming basically a minus A.
Yes.
Then how did we come after that? How did we conclude
So
this?
once AI becomes minus A, then what is this? Then this is minus A x1 plus minus A x2, so on, minus A plus minus A xn, plus A is as it is, whatever A we are choosing, plus xn, right? And
Yes,
this is
we
what?
get
This is, yeah, then this is 0 because this minus xi is getting cancelled with each of these.
but this okay, but this is not supposed to happen because AI is has a non-zero value.
Why, sir?
No, if it is coming to zero, then that can be only happen when all the scalars should be zero. But here we have a AI is a non-zero value, so
Yes,
therefore
because this is linearly dependent.
dependent. Right. Okay.
Yes, this is linearly dependent. That's why. For independent, we want to have, if one of them is 0, then all, sorry.
Hmm.
For linear independence, we need to have all of them must be 0. For linear dependence, it's okay. I mean, at least one non-zero, then we are through.
Hmm.
Okay, and that the next part of this statement is that if we choose any n of these vectors, then this becomes linearly independent. So let us check that. Let us, let me just copy this second statement. We have time. So we have to prove this, that if I choose any n of these, so if if we choose uh, so x1 to xn are anyway linearly independent. Okay, so x1 to xn, if I choose this a1 xn plus an xn, if I need this to be 0, then all this ai must be 0. Is that okay? If I choose this set, because
Yeah, that is fine.
yes,
Yeah.
that is fine, right?
Yeah.
Now, if I want to check that if we choose this set, x1, xi minus 1, xi plus 1, xn, and x1 plus xn. This contains n elements, okay? This set contains n elements. And now I have to check that this is now a linearly independent set. So how to check that? So if I take this ax1,
We have
a2,
included XI here, no?
yes.
One
So
element
one
we have
of them needs
excluded.
to we need to omit one of them at least. So
Okay.
I'm just for any I, this is happening. So if my I is 1, then the set starts with 2. If
Oh,
I is 2, it is x1, x3, x4, and so on, and x,
fine.
this element here. And now I'm taking ai xi minus 1. If if there is any doubt, please ask about this indexing. And if this does not feel good, please let me know. We can then prove for general statement plus some a into, again, I'm taking a as coefficient for this. I want this to be 0, right? So this imply we want this to be 0.
Ma'am, can you explain the indexing again?
Yes. So what we are doing, my set has, so my original set is this x1 to xn and x1 plus xn. So what I'm doing is I want to talk about n of this. So this set contains n plus 1 elements, right? x1 to xn and this last element. Let us call this one as x. So I need to talk about n of these. So the set where, so when I want to talk about n elements, then I have to get rid of one at each time. So when I consider only these n elements, first n elements, then this linear independence follows. Then it is linearly independent. Okay, so now I want to talk about the cases where this last element is there. Then I have to choose n minus 1 of these to have n vectors. So this last one is there, x as it is. Then I am omitting I of any xi from there for any I. So this is general form. So if my I is equal to 1, then this set becomes x2, x3, so on up to xn, and this x1 plus this x, or x1 plus x2 plus and xn. If my I is 2, then this becomes
x1, x3, x4.
yes, x1, x3, so on xn, and this last element.
Ma'am, but why
So
are we omitting one thing?
sorry, why are we what?
Why are we omitting a variable, like omitting one element?
Because we want to talk about every n vector of this set is linearly independent. But this set has n plus 1 elements. So to talk about n elements from this set, I need to omit one. So the given set, if you see the question, the family x1 up to xn, x1, x2, xn, and then this element here. So there are n elements if you see. This is first element, second element, third element. There are n elements here. These n elements. And this is n plus 1th element. And then they are saying every n of these vectors, because they know there are n plus 1 vectors. Then we have to talk about every n. So if I choose n from this set, I need to prove that those n forms linearly independent set. So what they are saying is, in this family of n plus 1 vectors, when I talk about all n plus 1 elements collectively, they form linearly dependent set. But this family is uh, it's quite not special, but it has the property that when I talk about n plus 1, the whole n plus 1 element, it is linearly dependent. But if I choose any n from that set, then it becomes linearly independent. So from the set of n plus 1 element, I now want to talk about set of n elements. This is what it means. This is what is asked here. So that's why when I'm talking about this set of n plus 1 element here, what are the possibilities? There are only n such sets, right? I mean n plus n or n plus 1. This this, then the next set will be of n elements. Next will be x1, or suppose x2 to xn, x1 plus xn. Second will be x1, x2, sorry, x1, x3, xn plus, comma x1, plus xn. So essentially, and essentially what we are doing, this x1 to xn, x1 up to xn minus, not for this, for this, minus some xi. That's what, right? For, when I'm talking xi is equal to x1, then it becomes this set. When I take xi is equal to xn, then it becomes this set. When I take xi is equal to xn, then it will become this set, x1 to xn minus 1, x1 up to this this element x. So when I wrote this here, let me try. Yeah, this one. I'm just omitting one. This is essentially this set here. Is this okay? Why we are removing that one element? Because from the set of n plus 1 element, we want to talk about n elements. Or let me. Is it okay?
Yeah, that's fine. I mean, any combination of n elements should be independent,
Yes. So this is just, we are choosing, let me write here, we are choosing n elements.
which basically says that another n plus one element could be one of the existing out of one elements.
Yes. Yeah, so we want this to be, we want, if this is 0, then this a1, an is equal to a to be 0. And how to do this? Note that, so if I combine this, what it gives me. So see, what we are starting with this ax1 plus a2x2, so on. Or if there is confusion, let me just, without loss of generality, let xi is equal to x1, and we will talk about a2 x2 an xn plus a. I will also write the general statement later on. Okay, now is it okay? I mean, Shreya, is it okay for you? I mean, that these
Yes,
are
ma'am.
n elements? Yeah, these are n elements now.
Yes, ma'am.
Yeah, you want to say something? I think no. So these are now n elements because this here are n minus 1 elements and this one extra. So there are total n elements. And see, I mean, if I combine all, so what this gives me, a1 x1 plus a2 plus ax2 plus, not a1, ax1 plus an plus a xn is equal to 0. So this imply what? If I compare both sides, then a must be 0. Comparing both sides. When I say comparing both sides, what it means is I I am essentially doing this. It means this 0 is actually 0x1 plus 0xn. So this gives me that a is 0, a2 plus a is 0, so on, an plus a is 0. So since a is 0 and all these things must satisfy, this implies a2 is 0, a3 is 0, and all this an must be 0. And that's what we wanted to prove, right? That each of these ai and a is a 0. So therefore, this set x2, xn, and this x1 up to xn is linearly independent because all the coefficients, because the moment I started with any linear combination, such that resultant is 0, the coefficient turn out to be 0 in each case, because this was general expression for any linear combination of these n vectors. And in general, if I want to write that, if I want to talk about that general expression, this was ax1 in general. The n vectors in general for n vectors, if I take this a1 x1 up to a I minus 1 x I minus 1 plus a I plus 1 x I plus 1, so on up to a n xn plus a into x1 plus xn, sorry, xn. If this needs to be 0, so what I get is this a1 a1 plus a x1 plus this a I minus 1 plus a x I minus 1 plus a x I, right? Here I have everything. Okay, everything xi and xn. This element is not changing at all. It is there as it is. This ai plus 1 plus a xi plus 1, and then an plus a is equal to 0. And this 0 was again, if as I wrote before, this is a1, this is 0x1, so on up to 0xn. Yeah. And I get a1 plus a to be 0, a2 plus a to be 0, and axi, so a must be 0 here. This a I minus 1 plus a 0, a I plus 1 plus a 0, and a is 0, and a n plus a is 0. And since this a is 0, this a1 to a I minus 1 becomes 0, and similarly this a I plus 1 to a n becomes 0. And overall I get that is all a1 to a n and a becomes 0. So we started with n element. This was general, again I'm writing this is general expression for linear combination to be 0. And from this and from above general expression, we need to be proved that all the coefficients are 0. Any doubt here?
That's fine.
Okay, so that's how we prove that the, yes, that given set is linearly independent now. The earlier one was linearly dependent. There we saw that the moment I choose non-zero A or any non-zero I get the whole combination of all the coordinates become non-zero. And here we saw that if we choose n of those, and if any linear combination is 0, then each coordinate, each coefficient of given vector becomes 0. Okay, so and now the second part. Second part is what we discussed earlier for this question, that let me just copy it from here. If there are any doubts, please let me know. Okay, so we have to prove that x1 to xn are linearly independent over K if and only if x1 to xn are linearly independent over K, and X does not belong to linear combination of the previous n elements. So when we say if and only if, it means if this is my statement P and if this is my statement Q, then I need to prove that P implies Q and Q implies P. This is Q. Okay, this is what we need to prove. So the first implication that x1 to xn and x are linearly, okay, linearly independent over K, and this is my given statement, and to prove that x1 to xn are linearly independent and x does not belong to kx1 plus kxn. And okay, so how to prove this? Any idea? Now what they did was they have given us bigger set, bigger information about the bigger set, and they are saying that that is linearly independent. And what they are saying is now its subset x1 to xn is linearly independent, and this x does not belong to linear combination of others. This x1 to xn and x does not really uh, what we say, uh, it's not much of a significance. I mean, you can just, so in general what this statement says is that if I take the general setup is x1 to xn are linearly independent if and only if x1 xi minus 1 xi plus 1 xn are linearly independent and xi does not belong to this. Why I'm writing this is, yes, what does this mean is that if I have bigger set of n or n plus 1 element or whatever number of elements you want, it's every subset will be linearly independent and no element from that set will be a linear combination of other element. That's what this statement essentially means. That if I have a set of linearly independent elements, its subset will always be linearly independent. That's the essence of this statement. Yes, you wanted to say something.
Um, Shall I say?
Yes, 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 please, if you want to.
I mean, it is clear, but if we look at the part A,
Yes.
if you look at the part A where it was at the family x1 to xn and x1 plus x2 plus up to xn is linearly dependent over k, and but every n of these vectors are linearly independent over k. So it means even though we do not include xi in the A and we included the last summation of all n elements, even then it is becoming a linear independent.
No,
Did I?
it was linearly dependent.
No, I'm any n elements of n plus one
Mm-hmm.
is becoming linearly independent.
Yes, yes, exactly.
It means if we include the last element, which was x1 plus x2 plus x3 up to xn, is also becoming a independent vector from the
It is
remaining.
becoming linearly dependent. So see, linear dependence and linear independence. So first statement, what it said that if I have bigger set, okay, if I have bigger set, and if I am saying that it could be if it is linearly dependent, its subset could be linearly independent.
It could
I
be,
had
could.
n plus one element; they were
Okay.
linearly dependent. but its subset having n element was linearly independent.
Right.
So a subset of linearly dependent set could be linearly independent.
Dependent. Right. Right.
But
Agree.
when we talk about linear independence of a bigger set, its subset has to be linearly independent.
Of course, because a bigger set,
Yes,
if all the elements of bigger set is linear independent, then any subset of this bigger set will be a linear independent.
exactly, exactly. That was the
My,
essence of first and second statement.
yeah,
The
my
first
question,
statements wanted to emphasize that the subset of a linearly dependent set could be linearly independent. Yes, sir.
yeah, my question is not that. I am little confused here because in the
Mm-hmm.
first question, the last element is the summation of all the previous elements.
Yes, yes.
So I am
This
just saying,
this one has nothing to do with that. This x is any element. This x is not equal to x1 plus xn. So the two dependent, sorry,
yeah. So
completely independent
yeah,
questions.
in the B part, it was said that if and only if x1 and xn are linearly independent over k and x does not belong to k of x1 up to k of xn.
Yes.
So this x is not. I am little confused
No,
here.
no, this x is not this. First of all, this x is definitely not this. And secondly, this x does not belong to linear combination of this. So what they are saying is that this x is not equal to a1 x1 up to an xn for any ai in k. This is what it means.
Um,
X does not belong to linear combination.
x does not belong to linear combination. Okay.
Yes. Yes. So it means they x, for example, uh, if I take this
So in the A part,
element.
in the A
Yes,
part, in the
yes,
A
sir.
part, can we replace the last element with like say kx1 plus kx2 plus kxn, something like this, or not?
So that so
No,
this
no,
see
my confusion is this. Even in B case, um,
this is a set. This is a set. That was element.
this is a set. Acha.
This is set. This is set. This is set of all linear combination of this type. A1 x1, A1 x1 plus an xn such that ai belongs to k. This is set, and that was element. And this element x1 plus xn, this belongs to this set if you observe, with 1 as coefficient of everything. Is this okay?
Um, okay.
Yeah. We'll try to prove this. And so the first is we want to prove that x1 to xn are linearly independent and x does not belong to this linear combination. So suppose x1 to xn are not linearly independent. Okay. So this imply there exists a1 to an in K with at least one AI non-zero such that I get a1 x1 an xn as a zero, right? But I can simply extend this to this a x 0, and this is now linear combination such that I sorry 0 x is this will be 0 with at least one ai non-zero, right? Because that's what we started with. So this is so this implies that x1 to xn comma x is are linearly dependent elements. But this contradicts my given assumption that these are linearly independent. Is this okay? If what I'm doing is I have linear combination, so this is like I want to prove for this, how to say this. So if I start with this set, what I'm saying is that I mean this is linearly independent set, and I'm just taking 0 here and adding extra. So I had linear combination of n elements, then I'm extending it to linear combination of 1 by just taking coefficient to be 0, and this still holds 0 because this was anyway 0. I'm just adding 0 to it with 0 into x, and the resultant expression is still giving me 0. But the coefficients here, one of them is non-zero from the assumption I made here. That happened because I assumed this statement that it is linearly independent. Okay, and that's not true. Sorry, it's not linearly independent. Sorry, I assumed that it's not linearly independent. Okay. So therefore supposition is wrong. Therefore our supposition is wrong.
No, but
Therefore,
when we say that in the statement which you just wrote it above,
hmm.
uh,
Which
it,
one?
I mean, the red circle you mark it, huh? If it is
Yes.
linear independent here,
Hmm.
it accent,
This.
yeah, you mentioned that suppose x1 to xn are not linearly independent,
Yes, because
then
that's what we wanted to prove.
that is okay. But such
Yes.
that when you write such that a1 x1 plus dot 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 a and xn, this should instead of equal to 0, this should be not equal to 0 here, no? Because that
Not independent means linearly dependent, right? And for linearly dependent,
the summation of
everything,
all elements should not be equal to 0.
it must be equal to 0. It must be equal to 0, but AI must be non-zero.
Acha, acha, okay.
So the addition is 0, but coefficient is non-zero.
Okay, okay.
Yes. So here this equal to 0 is always there. See, in the definition also when I wrote
I got
this,
it. I was just
yes,
confused.
yes.
Not okay.
Yes. Mhm. Let me just mark this that this is always 0. The combination here also it is 0, but the difference
Coefficient is
is
non-zero. Yeah.
yes, the coefficients whether they are 0 or not. For independence it must be 0. For dependence it must be non-zero.
At least one of them
At
will be
least one of them must be non-zero. Yes.
okay.
Here also I wrote at least one of them is non-zero. Okay. So that's happening. And next they are saying that I want this x to not belong to the linear combination. So suppose x belongs to this kx1, this kxn. So this is proof by contradiction. We assume something uh, which is, I mean, which is what we say negation of the given statement, and then we arrive at a contradiction. And we arrive at that contradiction because we assume something that's not true. And that's how we are trying to prove these statements. Here also we assume that x1 to xn are not linearly independent. Then we arrive at this contradiction that this bigger set become linearly dependent, which was false from the given assumption because this set was linearly independent. So our supposition was wrong, and this set of n elements now become linearly independent. Now we are doing the same thing. We are assuming, suppose that x belongs to the linear combination of these n elements. So this imply what? There exists a1 to an in K such that this x is equal to a1 x1 an xn, right? This is what this statement means. This means this. Let me just write whole thing down here. Okay. And then I can do this minus a1 x1 so on minus an xn plus 1 into x is equal to 0, right? So this is linear combination of x1, x2, xn and x. And one of the coefficients is non-zero, right? This 1 is non-zero. This is non-zero linear combination x1 to xn and x such that minus a1 x1 minus an xn plus this 1 is non-zero, it's 0. This contradicts the linear independence of x1 to xn and x. Okay, so therefore our supposition was wrong.
Ma'am, why is 1 the coefficient of the last element?
Because see, from given statement, this is there, right? This is true. This is true from our assumption. This is true, right? So I'm just shifting everything to the left side. And when I shift everything to the left side, I don't care. What I want is to declare something is a linearly dependent. I want at least one of the AI to be non-zero.
Wait, ma'am,
And I don't, yes.
ma'am, why is x equal to the linear combination? X is the nth element, right?
No, it is given. So see, we want to prove this, that x belong to, we have to prove that x does not belong to this set. This is what we want to prove. So what we did is we assume that suppose it belongs. We want to prove that, see, we want x to not belong to this thing. So what we did this is called as proof by contradiction. So there what we do is we assume something opposite of what we want to prove. Or opposite means negation of what we want to prove. So what we do is we assume x belong to this kx1 to kxn and arrive at the contradiction. Contradiction means something that is not correct based on the given assumption or hypothesis. So what we did is we assume that suppose x belong to that linear combination kx1 up to kxn. And what does that mean? That there exists a1 to an in case such that this x can be written as linear combination of this x1 to xn, right? When we wrote earlier that
That it can be, assume it to be a linear combination of all this, and then we find that it's contradictory.
yes,
Therefore,
I mean
it's not.
this is element, okay? This is now element. This is element. And this is set. When I write this A1 to AI are I mean, there are some elements from K. So for example, in a very first example, when I chose this 1 comma 1 comma 0 belongs to my U and which was K, I think we got that 130 plus. We do not care. I mean, what I was saying this AB0 belongs to U and we saw that it belongs to K1 R1 00 plus R 0, 1, 0, right? So this is now set. This is my set. This is equal to u, and this is my element. So when I'm writing this, when I'm saying that some element belong here, it means, so this is writing this. If I take this x1, this x2, and this is my element x, so x belongs to kx1, kx1, kx2, right? And
Yes.
this x, yeah, this x is ab0. So what will be my a1 and a2? So when I'm writing this x belongs to this, means this x is a1 x1 plus a2 x2. And what this a and when I have expression of x, I can talk about this, what this a1 and a2s are. So when I am saying that this x belong to this set, there exists some a1 to an. We don't know what that is, but there exists some a1 to an in case such that this x is equal to this expression. That's what we are doing here. We did here. We did in the first question. Okay.
Yes, ma'am, it's clear.
Yes. And now I wanted some non-zero linear combination. That non-zero means at least one of the AI. When I'm saying AI, please don't take it AI to be here. I wanted coefficient of at least one of the vector to be non-zero. Okay, and the coefficient of this, so if I want to call this a n plus 1, this a n plus 1 is my 1 now. So what I'm trying to say here is, if I am writing this as a1 x1 up to a n xn plus a n plus 1 x to be 0, then that this a n plus 1 a n plus 1 is 1, which is giving me non-zero linear combination of x1, x2, xn and x such that uh, this expression is 0. Okay. And but once I have this expression to be 0, it means that this x1, x2, xn and x are linearly dependent. But that contradicts the given fact that this set is linearly independent. That is given to us. Okay, so that's why what we assumed is not correct. So when we arrived at this contradiction, and that's why we can say that x must be in. So it is like when we assume something wrong, it will lead to something wrong, like that. And it led to something wrong which was actually completely correct as per the hypothesis. So that should not happen, and that happened because we assumed something wrong. That's the proof by contradiction in nutshell. Okay, is that okay?
Yes, ma'am.
Okay, so now the we will just prove the, we are over time, but for the what we say, the other implication, we have to do the same thing. We will just assume the linear combination, and we will take two cases: when coefficient of x is 0 and when coefficient of x is non-zero. If coefficient of x is non-zero, in that case, this will happen, and I can say that it is linearly independent. And if the coefficient of x is 0, then it is just linear combination of this first n elements, because I can omit x in that case. And then if that has any non-zero element in it, the coefficient in it, then it will contradict the this statement that x1 to xn are linearly independent. And that's how I will get the entire set x1 to xn and x is linearly independent. Is that okay? Do I need to write that?
No, ma'am, it's okay.
Okay, it's okay, right? So there are any doubts now? because we are over time, and you can I'm pretty sure you can solve this third question as well, which is asked here. This is about generating set, which is pretty, it is different. I discussed what generating system means in first question, so try to uh, understand how this is working. Okay, if there are any doubts, please raise those in the discussion forum, and we can stop if there are no doubts.
Fine.
It's fine, right? Okay, so if you have any doubt, please raise those in the discussion forum, and we can stop the session now. Yeah. Thank you.
Thank you.